After a brief introduction, I will talk about the theory of anisotropic laminated and latticed shells. I will speak about the numerical technique that I use to solve this kind of problem. I will introduce numerical implementation, and I show you an n-order shell finite element formulation. And after that, I present to you application and results, and I finish with conclusion and perspectives. This lecture is based on three basic aspects. Two of them are theoretical. One is the generalized higher-order theory that allows us to study anisotropic doubly-curved shells using a unified formulation. The second one is the differential geometry that allows us to describe the physical problem. And finally, a computational aspect that allows us to approximate the derivatives and the integrals in order to discretize the complete system of equations. The main bibliography is reported here in this picture, and from these books that you can see in this slide, you can find all the theoretical aspects that I will show you in this lecture. If you want to reobtain all the results that I show you in this lecture, you can use the HOOKE'S software, and you can download for free from the link presented in the slide. Now we can start for the theory of anisotropic laminated shells, and we want to consider in particular moderately thick shells with the range represented in the slide, and we start from the definition of the position vector of the reference surface of the shells, and using the differential geometry we can evaluate the Lamy parameter, and after that we can evaluate normal vector, and finally if we consider orthogonal curvilinear coordinate system we can evaluate directly the principal radius of curvature. After that, if we want to approximate the displacement field inside the solid, we have to introduce the kinematic model in a unified formulation way as represented in compact form here. This unified formulation allows us to consider the effect of some special effects such as the zigzag effect if we use Murakami function. The approach is an equivalent single layer. Here are reported the expanded form of the formulation presented before in one example regarding an 18 degrees of freedom, and using these families of theories and formulation we can obtain as a special case the first shear deformation theory, such as a theory with 5 degrees of freedom. Here are reported the classical thickness function that we can find in literature or some example, and here I want to show you the notation I use to represent the equivalent single layer approach I use in this lecture, and in particular I want to highlight that the approach is based on the generalized displacement defined along the reference surface of the shells. After that, I want to show you some example. One of them is a classical example using as a thickness function the power series, and then a very complicated example. In particular, we use an hyperbolic sine, hyperbolic cosine as an approximation of the field along the thickness of the shells. And another example, very complicated, and in order to highlight that we can consider different terms of expansion in the three directions of the coordinate shell surfaces. After that, if we start from the analysis of the strain, we have to introduce the strain components, and if we introduce inside these strain components for the 3D shell solids, we can obtain directly by using the kinematical model presented before the generalized strain definition reported in the slide. After that, we have to introduce the constitutive equation in order to consider laminated composite shells. And we refer directly to the linear elastic material, and in particular, we can consider anisotropic material with 21 elastic constant, independent constant, and the classical orthotropic and isotropic material, and very complicated materials such as functional gradient material. In particular, from this material, we can have a smooth variation of the mechanical property through the thickness of the layer. Now we have to introduce the constitutive equation and the classical transformation of the material coefficient to define the generalized internal action in terms of generalized strain, and we have to define the engineering elastic constants are reported in the slide that we evaluate numerically for each point of the reference surface. But I want to highlight some particular important aspect to this approach, because using this approach, we can consider that the mechanical properties of each laminate can vary along the three principal directions. So we can have this kind of elastic coefficient, and we can consider that the thickness of each laminate can vary along the two principal directions due to the fact that the thickness of the shell can be variable. But to consider in the model this kind of variation, we have to evaluate the derivative of the engineering elastic constant numerically. So I need a numerical technique to do this mathematical operation. But if we want to obtain the motion equation natural boundary condition, I have used Hamilton principle, and I have defined the external action that acts along the top and bottom surfaces of the shells. Now, in this picture, I represent the three governing equations for each index tau, and the boundary condition I have obtained using the application of the Hamilton principle. But if we want to consider a complete shell of revolution, we have to introduce other boundary conditions. In particular, I refer to kinematical and physical compatibility condition reported in this picture in order to obtain as a special case the shell of revolution, special case of the panel of revolution, for example, in order to maintain the problem completely two-dimensional. And so we can, using this approach, we can consider this kind of structure reported in these pictures. After that, we can write the fundamental nucleus in terms of displacement defined along the reference surfaces, and then we can assemble the complete system of equation. But now we have to introduce a numerical technique to solve this differential system of equation. And in particular, I have used generalized differential quadrature method. This method allows me to approximate the n-order derivative of a function using this linear sum, and the special aspect to do this approximation is the definition of the weighting coefficients. And if we use particular basis functions such as Lagrange polynomial, we have an important properties. The matrix A becomes an identity matrix, and in this way we can evaluate the weighting coefficient for the approximation of the derivative exactly using this relation. After that, if we want to shift from the definition interval to the physical domain, we can use this simple relation to do this operation as reported on the slide. And if we want to evaluate for any derivative order and for any grid distribution the weighting coefficient, we can use this simple recursive relation proposed by Schur during the time. And but if we want to evaluate the integral of a function, we need another important tools to solve this problem. And here I introduce this a numerical tool. Also, for this case, the important thing is how to evaluate the weighting coefficient for the numerical evaluation of the integral inside a closed interval. And to do that, we can consider this relation. As you can see, we can use the weighting coefficient for the first order derivative to evaluate the weighting coefficient for the integration numerical scheme. And then, if we use this simple relation, we can evaluate the integral of a function in any kind of closed interval. After that, due to the fact that I want to study very complicated shell geometry, I can start from the mapped geometry and introduce a mapping technique to consider and to pass through the parent space in order to obtain this distorted geometry. To do that, I want to introduce the mapping technique, and to obtain this mapping, I use a blending function as reported in the slide, and I have to introduce also the Jacobian of the transformation to evaluate all the parameters that I need to do this transformation. To describe the curvilinear edges of the patch, I have to introduce, for example, and I use NURBS curve that have this important property I reported in the slide, and so I can study this complicated geometry. But I have to also introduce another important aspect, the boundary condition on the curvilinear edge that I reported in this picture. Now, up to now, I have proposed to you the strong formulation, but I want to propose another formulation, the shell finite element formulation in particular. And if I use a Lagrangian polynomial approaches and I approximate the field inside the element using this polynomial, I can introduce the vector of the unknown, and then using the Hamilton principle or Venetian formulation, I can define directly the stiffness matrix. It's important to notice is that to evaluate the stiffness matrix in all the points of the reference surface, discretizer or obviously in discretizer form, I need a numerical technique, in particular numerical integration technique, as I exposed before in this lecture. Also, I have used kinematic operator as reported in this picture, and then I can define also the mass matrix and external forces. Now, if I want to consider the dynamic analysis for this kind of problem, I have to solve the classical eigenvalue problem in discrete form. And if I want to study the static analysis for this shell structure, I have to solve a classic linear problem as reported in the slide. Now I skip directly to the application and result for this kind of structures. In particular, I will present a strong formulation isometric analysis. I have considered here a catenodal panel. I cut the distorted domain using a rhomboidal shape, and I have considered a very complicated lamination scheme, 3045, and I have considered 2 layers made of anisotropic material with 21 independent constants. The material is reported in the slide is a triclinic material, and I have compared result for this structure using 3D FEM commercial software such as Abacus and different kind of higher-order theory as reported above in these lectures. Here I have reconstructed the mode shape for the first 6 mode shape for the structure I have considered and for the boundary condition I have considered. But if we want to use a very complicated shape, I have considered in this case a cylindrical panel cut by this generalized shape with 2 curvilinear edges and obtain this complicated geometry. And here I report the result for different higher order formulation and for different kind of boundary condition. I have compared this solution using a 3D FEM software, and in particular I have used a 20 node brick element to obtain the solution. Here I reported other mode shapes for this kind of structures. But if I want to compare strong formulation and weak formulation, here reporting a very complicated example. I have considered laminated double-curved shells, and I have cut the distorted domain using this geometry and obtained these final shell structures. And here I have compared the strong formulation and the weak formulation using different kind of higher order theories, and I have compared the solution using the 3D elasticity solution for a very complicated lamination scheme as reported on the slide. I have considered here the first mode shapes that I have obtained using the CUMASPAM, and here I've changed the lamination scheme and the material and the boundary condition, and as we can see I have obtained very good agreement also for these generalized shape structures. Here I reported also the mode shape that I can reconstruct using my software. After that, I want to show you another application, in particular at the general plate with a linear variation of the thickness. I have compared results from the strong formulation and weak formulation, and with the 3D elasticity solution using Abacus. As we can see, I have obtained very good agreement also in this case. And here I reported the first mode shapes that I have obtained using my software. After that, I want to speak about some complicated material, in particular lattice shells. I have considered different kind of cell, and in particular, for example, I have a sandwich panel with the core made of an isogrid cell, hexagonal cell, or rectangular honeycomb, a rectangular cell or square honeycomb, and auxetic cell or entrant honeycomb. And for the first case, I have reported here the mechanical properties that I have used to homogenize and to obtain the orthotropic materials. And here I report results and the comparison between different kind of theory in terms of the first 10 frequency I have obtained from the FEN model and the theory I have proposed before. Here I reported other case, in particular comparison from the literature, in particular for a cylindrical shells and for a cylindrical panel, by changing the angle of the ribs of an isogrid core. And finally, I propose to you a parabolic paraboloid example using different orientation of the ribs and different kind of theories. Finally, for this kind of material, I have considered honeycomb cell with 3 scheme, and here I reported the material property that I have used to obtain the equivalent orthotropic material, and here I reported the result of the comparison between the 3D FEM with the higher order formulation I have used for the hexagonal cell, for a rectangular cell, and for auxetic cell. As you can see, I have obtained very accurate results by this comparison. Now I want to speak about another topic regarding curvilinear reinforcement fiber. Here I have considered that a variation of the fiber orientation using this relation, in particular a 2-parameter a variation of the orientation of the fiber. Here is reported the notation, and in this picture I present some special cases by changing the parameters, and in this picture we can see the orientation of the fiber along the reference surfaces. But I want to show you an application. I consider a conical shell and 2 different schemes, and I show you the variation of the fiber orientation both in the center along in the edge of the conical panel. And here I represent the sensitivity of the structures in terms of the first 10 frequency by varying the orientation of the central point of the laminate. And here I represent the sensitivity of the structures, of the response of the structure in terms of the first 10 frequency by the variation of the orientation along the edge of the lamina. And here I reported the mode shape that I can evaluate using the CUMASPEB. After that, I want to show you a parametric study for the free vibration of laminated elliptic paraboloid. Here I have considered a 3-layered structures, and I show you the sensitivity of the response of the structure by changing the parameter phi. And here I have reported this for this case, this sensitivity in terms of the first 10 frequencies. And here I reported also the first mode shape for this kind of structures. But I have introduced during the time a new general variation of the fiber orientation. As you can see, I can superimpose 6 different functions. For example, a power function, a sinusoidal function, an exponential function, Gaussian function, an elliptic function, and then I can obtain this different and very complicated path from the orientation of the fiber along the reference surface of the shells. And here I reported some example and complicated example for this kind of variation. But for the first case, I have considered an hyperbolic paraboloid, and here I show you the sensitivity of the structures in terms of the first natural frequency if I use linear and sinusoidal variation by varying the parameter phi. And here I have considered a linear variation of the fiber orientation along the alpha 2 direction. And here I reported the mode shape that I have evaluated using the CUMASPA software. And here I want to show you a new result. In particular, I consider 3-layer structures with the lower sheet is made of angle toe laminate using this path, and the upper sheet is made using this path, and the core is made of foam. And here I reported the comparison between the 3D FEM solution. In particular, when we consider phi equal to 0, we have the classical laminated composite shell, and here we can see by changing this parameter and changing the theories, we can see the sensitivity of the structures using this kind of variation of the fiber inside the shells, inside each laminate of the shells. And here I reported this variation versus the parameter phi for the first 4 frequencies of the structures using different kind of theories. And here I reported the first 3 mode shape for this kind of structures. After that, I want to speak about the carbon nanotube. Here I reported the law that I used to graduate the material along the thickness, and as you can see, I have introduced 2 different agglomeration parameters. In particular, I have mu and eta, and as agglomeration parameter, and I use a Mori-Tanaka scheme to evaluate the mechanical properties, along through the thickness of the laminate. And here I reported the formulation I used to do this operation. Here I reported also the mechanical properties of the carbon nanotubes and the polymeric matrices, and then I start to consider the first case. I consider elliptic paraboloid, and I show you the sensitivity of the structure in terms of the first 10 frequencies when I fix the first agglomeration parameter mu and change and vary the second parameter. And so if we consider the second parameter fixes and vary the first parameter, we can see the variation in terms of the first frequencies. And so if we fix the 2 agglomeration parameter and we change the exponent of the power law of the distribution of the volume fraction of the carbon nanotube inside of the lamina, we can see this sensitivity of the response of the structure. Finally, I have considered a very complicated geometry, and I have considered 3 layers. 2 of them are made of functional graded carbon nanotubes, and I show for different kind of mass fraction agglomeration the variation in terms of the first frequency by fixing the second agglomeration parameter eta by varying the first one. And here I represent the same thing by fixing the first agglomeration parameter and change and varying the second one for different value of the mass fraction. After that, I want to show you the last topic of this lecture is regard the damaged laminated composite doubly-curved shells. Here I have represented the model to that I use to modeling the damage, and in particular I have considered that the material properties can decrease in a small area, for example using Gaussian function of ellipse shape function, and I skip directly to result. In particular I have considered a rectangular plate. For the first case we can see the result in terms of a response of the structure from the damage configuration for different level of the damage, using different kind of higher order theories. Here I have considered the effect of the area of the damage, and we can see the response of the structure from undamaged and damaged configuration by increase the area of the damage. And here I have increased the number of layers that have the number of the damaged layer. In this case we have the undamaged configuration, and here we increase the number of layers that present damage. Also, I have considered another parametric studies when I have increased the area of the damage. Finally, the last example is regards to a completely doubly-curved shell panel. Here I have considered 4-layer structures, and here I reported the response of the structure in terms of vertical displacements and tangential displacement when I have increased the number of damaged layers. Finally, I will skip directly to the conclusion. And so the proposed approach for the analysis of two-dimensional structures has allowed to analyze anisotropic composite lattice shells and panel of various geometrical shape, has allowed to study the behavior of generally laminated composite shells and panels characterized by various lamination schemes, has shown the influence on the dynamic and static structural behavior on the choice of power law distribution for laminated made of functional graded materials and carbon nanotube materials, has provided results very close to those obtained by various commercial FEM programs such as Abacus, has produces accurate and reliable results for all the boundary conditions and for the whole grid distribution considered. As a future development, I want to study, for example, these complicated structures such as compound shells. I want to introduce crack and discontinuity, forces vibration, and want to consider magneto-piezoelectric materials and the effect of thermal variation. And in fact, in the future, I want to study very complicated shell structure using weak and strong formulation as I presented in this lecture. I want to highlight again that if you want to obtain this result, you can download for free from this link the software that is completely free. And I want to thank you for your attention.